On a gloomy day at Cape Canaveral Air Force Station in 1987, a U.S. Navy communications satellite launched on its way to orbit. But only 48 seconds into this flight, the rocket exploded in the clouds above the launch site. That resulted in the loss of nearly $200 million worth of hardware, and the implications for the ultimate cause of this accident are critically important for how aerospace engineers write and manage requirements. Welcome back to Engineering Aerospace with me, Eric Kane. And in today's episode, we're talking about Atlas-Centaur 67 and the implications for how engineers write and manage requirements. Now, on this particular launch, there was an interesting controversy that occurred, and it really revolved around a particular launch commit criteria. So on the day of this launch, there were continuous weather events, so storms and cloudy weather around Kennedy Space Center, which is not terribly uncommon in Florida. You get a lot of, storms and rain and that sort of thing. And so on this particular day, the rocket and everything was basically ready to go, but the launch team was hung up on a particular criteria that was stated as such. The flight path of the vehicle should not go through mid-level clouds 6,000 feet or greater in depth when the freezing level is in the clouds. So what does that actually mean? Well, that's basically all the information the team had to work from, right? Was the criteria. So when you're reading at this requirement, they're trying to figure out whether or not this really is a limiting factor for the launch, right? Well, there's a lot of money, a lot of energy put into, bringing a rocket up for a launch, and to cancel it for weather is always a disappointment. But you have to make sure that the conditions are safe. Otherwise, you're going to end up with an accident. So when the team was looking at this, they evaluated it from the standpoint of what information did it have in front of them. Well, it talks about clouds with a freezing layer. Now, without any further information, you probably are thinking, okay, the freeze layer could result in icing, right? So, they basically called over to, some of the pilots in the area that had flown in for the day, tried to check and see if they had experienced any icing on the way in. There was nothing reported. I think they actually sent another aircraft up to go check the conditions, flew through the clouds, and did not report any icing conditions. And so even though the weather conditions had reported that there was an exceedance in the case of this criteria, meaning that there was a freeze layer in clouds greater than 6,000 feet in depth, well, they decided, since there was no reported icing by the pilots that flew through these conditions, that they were going to basically set that requirement aside and they were going to launch anyway. Now, what happened probably wasn't immediately obvious, but when the rocket launched, 48 seconds in, system glitched, the rocket hard over and basically broke up in flight. Upon further investigation, it was pretty quickly obvious that the rocket had actually been struck by lightning. Now, why is that important? Well, obviously, lightning striking any vehicle can cause all kinds of problems. But in this case, it actually corrupted one of the memory bits in the guidance system, caused the rocket to change direction suddenly, and basically broke up from the aerodynamic forces. The range safety officer supposedly commanded an abort to destroy the rocket, but the command never reached the vehicle because it had already disintegrated by the time it got up there. So, basically this lightning strike is what caused the rocket to fail. Now, when we go back and we look at what causes lightning to react or to attach to a vehicle, this is not the same kinds of conditions that you might think of with a typical lightning strike in just nature. So I'm going to go to the tablet here, and we'll kind of talk about how lightning can impact vehicles. Now, I do want to point out that this applies both to aircraft and spacecraft. So let's talk about lightning. So lightning, if you have a ground of the Earth here, and then we have some sort of clouds above it, lightning is usually the result of some sort of charge differential. Now that may be positive or negative charges. I'm just going to draw them here this way. And that, can result in some sort of lightning trying to bridge that potential gap. Now, what causes that potential to arise in the first place? Well, usually that is a result of some sort of convection forces. There are usually, bigger the clouds, there tends to be more convection. There's a lot of turbulence in there. And what you have to create that charge is usually some sort of particles bumping into each other and transferring charges. So this frequently happens with ice particles and rain droplets. And so if you have the right combinations of these, one particle may be going up, the other's going down, and they start to bump into each other. And what you can get is a separation in charge from the top and the bottom of the cloud. This can also occur in different areas of the cloud. You may get more negative charges in one portion, positive in another, and this is what typically results in some sort of cloud-to-cloud lightning. Now, how does that apply to this particular situation? Well, there can be conditions where the potential difference here is not enough to cause an actual natural lightning discharge. So what you end up with is you have these potentials that have built up, but they're not strong enough to bridge that air gap, right? It can take millions of volts to be able to bridge the thousands of feet that these lightning bolts have to travel. So, however, when you start launching a rocket or putting an aircraft into this situation, you have a rocket launching up. Let's just have this little rocket down here is flying off the launch pad. Well, now you have a large metal structure that is flying up through these conditions. And I'll change the color here so it stands out. But you have some sort of rocket here coming up through the cloud, and now you've basically reduced the resistance, right? There's this air gap in here. Air is a good insulator, but a big metal tube makes a very good conductor. And so suddenly, these negative charges now have an easy way to get back down to the positive charges. On top of the fact that you have a structure in the vehicle that is conductive, you have this exhaust gas that is usually come out of the rocket and is charged, high energy. It may be still a plasma when it's close to the rocket. Even if it's not, you've got particulates and things. This actually makes a very good conductor compared to the air. And so what usually happens when a rocket gets struck is that you'll see this charge come all the way back down to the launch site because it's taking the path down the exhaust trail. Now, you can get a similar situation if you're flying an airplane, right? And you fly that airplane into this cloud. Again, suddenly you can get a situation where perhaps a lightning bolt will attach, and usually it kind of comes in the front or back of the aircraft and goes out the other end. Now, in this case, of course, you're horizontal versus vertical, but very similar situation occurs where the conditions may not be enough for a natural lightning discharge, but the simple presence of a conductive structure and the gases from the exhaust can actually make it conductive enough to allow that discharge to happen. And this is what we call an induced lightning strike. So it wasn't going to happen naturally, but you've induced it by the presence of the vehicle. Hey, real quick, if you're an early career aerospace engineer or maybe even a student, and you'd be interested in interacting with others at the same stage, well, I've set up a community space where you can ask questions, share stories, or just shoot the breeze when it comes to things going on in the aerospace industry. It's totally free to join. Just check out the link below and we'll see you there. So what does this have to do with how engineers write requirements? Well, it turns out, this is not the first time that a rocket has been struck by lightning. In fact, the requirement that was written that stated the the need to avoid the freeze layer in a 6,000 foot cloud layer. And again, if let's say there's a freeze layer in here, that means you're going to have ice particles up here and probably rain droplets down here. And again, that goes back to that creates that potential. So what that requirement was telling us was there's a potential for the lightning strike to occur because the conditions are set up that there's a large charge potential. And while that wasn't written into the requirement, it was developed as a result of a lightning strike on the Apollo 12 mission. So if you're not familiar with that, on the Apollo 12 flight, that rocket launched in similar conditions. 3 astronauts on board on their way to the moon, and it got struck, and a large portion of the vehicle systems shut down or were corrupted. They're in the middle of flight. Fortunately, the crew commander, kept his cool, worked it with Houston to try and figure out what they were going to do. One of the engineers on the ground recognized a similar issue they had seen in practice and called up a command, said, hey, let's try SCE to aux, which basically reset, a power source to an alternate power source. And with the flip of one switch, the whole system came back online. Now, that was fortunate. They got away with that one. Fortunately, the primary guidance for that rocket stayed intact. It was just other systems within the vehicle that had problems. But as a result of that lightning strike, they implemented new rules to help prevent that from happening again. So what does this mean for you and how engineers write requirements? Well, I think there's what I've seen as a cycle. I saw this kind of based off of a meme I saw recently as a result of some other issues, but you can kind of think of this as a cycle. And the first part of this cycle is rules are put in place, right? So this is basically what happened after Apollo 12. They said, hey, we found there's a problem here. We need to establish a rule. And this rule is now our criteria by which we're going to launch rockets. So years go by, this is put in place, folks follow it. And then as time goes on, people forget. Human brain's not very good at remembering things, first of all, but it's even less good when you're trying to communicate from person to person, generation to generation. So even though these rules were put in place and some folks probably recognize them for many years working, eventually there are people doing these operations that are not familiar with the original reason. So what happens next? We just throw it out. Oops, there should be an R there. Throw out. So we get rid of the rule. Well, we don't understand why it's there. Why do we still need it? Let's get rid of it. And then, of course, what happens? Something goes wrong. Failure occurs because we stop paying attention to the rules that we wrote. Got to go back, write new rules. So how do you break out of this loop, right? How do we get away from getting stuck in this cycle? Well, my suggestion is we put rationale. So what I'm saying is that when you create these rules, you not only write the rule, but you write the rationale as to why the rule was put in place. Now, this applies just as much to writing requirements for a new design as it does to designing, flight commit criteria for a rocket. Basically, what you're doing is you are not just writing what you need to happen, but why are you putting this rule in place, so that when folks come down the road and are not familiar, were not involved with the original writing, that they can understand why this was put there. So if that requirement that was placed on this Atlas-Centaur flight had a rationale next to it that said, this is in place to protect against lightning conditions that could strike the rocket if this particular condition is present. That would have been different. That would have told that that launch crew that, looking at whether or not there's icing there has nothing to do with it, right? This is put in place because these conditions can generate lightning that can strike a rocket on the way up. And so you can apply this in many different types of conditions, right? I've seen situations where we had written requirements for a new design, and 2 years down the line, we're going back questioning whether or not we need a requirement, but no one can remember why we wrote it down in the first place. There may be a situation where, okay, maybe you do want to keep that because of, in this case, right, there's valid rationale as to why that was put in place. But you may also need the opposite, right? You may be able to look at the rationale and say, oh, this is why we had this in place in the first go round, but it's no longer applicable. The rationales no longer apply to what we're trying to do, and so therefore we can take it out. And so it helps you in both directions, right? Is not just maintaining the rule, but also helping you determine when removing the rule or requirement would be appropriate. So that is the short of the lesson learned from this particular launch failure, and how you can apply that as an engineer in your day-to-day job. I'd suggest, if you are writing requirements, if you're writing rules, flight restrictions, etc., that you consider making sure that there is a rationale listed with every requirement that you can, because then it helps those people that were not there when it was created to understand the reason behind that. That's all for today. Thank you for joining me, and we'll see you on the next one.